Hi, this is the TheoryStation. I'm John Duggan, and this program is called Rational Choice Modeling. The series that we're in now is the Basic Formal Theory Toolkit, and this is the 10th installment in that series. In the previous couple installments, we were talking about the model of the consumer, which has an economics kind of focus. A distinguishing aspect of that model is that the object of choice is multidimensional. We looked at a case of two goods, so a consumer was choosing two quantities subject to some budget constraint, and that model is easily generalized to any number of goods. So what I want to do now is swing back to a more political science focus, but to carry that multidimensional feature. In the past, we talked about a model of politics where policies were one-dimensional. So there was a one-dimensional policy space, which we could think of as being on the real line. And that is a workhorse model, and we spent a lot of time on it. In terms of applicability, it's a good model to to test ideas, and you can definitely get a sort of broad picture of politics in terms of one dimension. A lot of times analysts think about an ideological spectrum, and one end of that might be more conservative policies, the other end might be more liberal policies. And it's true that in sort of common discourse, or when we're looking at journalistic reporting, we do often, characterize policies as being more conservative or more liberal. But if you look more closely, if you look at the policy platform of a candidate, for example, it's going to be quite a bit more complex than just, I'm a moderate, right? There's a lot of different policy dimensions that we think about. There's taxes, there's healthcare, there's racial justice, gun control, regulation. I mean, the list goes on and on. So, when you look at it more closely, the world is highly multidimensional. So what if we want to think about a more realistic model, a more fine-grained model of politics, where we're actually explicitly accounting for different policy dimensions rather than collapsing everything into just a single policy variable? Well, there's a standard model for that, and it's in some ways a straightforward generalization of the one-dimensional model. So we're going to be looking at the multidimensional policy choice model. And once again, I'll start by specifying the set of possible choices. We use the notation X. And now there's different variations of this, but just to keep things simple, I want to think about a model with two policies. And I'm just going to let these policies take I should say two policy dimensions, and I'm going to allow those positions on those two dimensions to take any real values. And so our policy space then would not be just the real line, but it would be pairs of real numbers. So we use this notation R2. So that's just any pair of real numbers, x1 and x2, where x1 and x2 belong to the real line. Obviously, geometrically, we think about this as the Cartesian plane, right? So now that is our policy space. It's not just a one-dimensional set anymore. And well, now that we're thinking about a two-dimensional policy space, well, we need to talk about preferences over that, right? We're thinking about let's say a politician who has to choose policy. Let's just extend the simplest idea of Euclidean preferences to this model. And so what I'm going to do is I'm going to assume that the politician has an ideal point P, and now P will belong to this, it'll be a pair of numbers. Geometrically, we can think of it as lying in the Cartesian plane. So there's going to be, we said there's two coordinates of P. The first coordinate is P1, the second coordinate is P2. You can think of P1 as being the politician's ideal position on the first issue, and P2 is the ideal position on the second issue. So all right, that's an ideal point, but now how do we think about the politician's preferences? As in the one-dimensional model, I'm going to assume that the politician just likes policies that are closer to his ideal point. So what does closer mean? Well, if we need to talk about how to measure distance on the Cartesian plane. Suppose I have a policy, let's say x. Well, it's a pair, so let's call it x1, x2. How far is that from the ideal point? Well, the measure of distance that we're going to use, it's the standard one. And let me just write this out. The distance of a policy. Now I'm going to instead of always writing x1, x2, I think I'll sometimes just write x with no subscript. X with no subscript will be the notation I use for a pair of numbers, x1 and x2. So x1 and x2 are the coordinates of x. So the distance of x from this ideal point is, well, what we do is we look at the distance on the first dimension, and we're going to square that, and then we look at the distance on the second dimension and square that. Let's add those together, take the square root. That is our measure of distance. That's really, the standard way of doing it. It's called, it's called Euclidean distance, or the Euclidean norm. The notation that we'll use for that is to put, P minus x with two vertical bars. So this notation, P minus x with these vertical bars on either side, that will denote the distance between P, the policy P, and the ideal point P and the policy x. And it's defined by this formula here. Okay. We could spend a lot of time on this, but really, this is just a special case of the Pythagorean theorem. I won't go into that, but there's nothing magical about this formula. That's just how we measure distance between 2 points on the Cartesian plane. Okay, so we're going to assume that the politician has, we can think of it as a list of preferences, which I'll use big P for, and between any two policies, so here X is a pair, X1, X2, Y is a pair, Y1, Y2. So between any two policies, X and Y, our politician will like X more than Y as long as, or whenever, it's closer to the politician's ideal point than Y is. Okay, so this inequality that I've drawn here means X is closer to P than Y is. Okay. This relationship is, it's an if and only if, meaning that, you know, if X is preferred to Y, then it's closer, and vice versa. If X is closer, then it's preferred. All right. So we have, we've defined what our policy space is, and we have our definition of preferences. We're going to call this, again, Euclidean preferences. Okay. Now, before I go on here, let me just extend the idea of utility. So, as we know, a utility function is just an assignment of numbers to every possible choice, where better choices have higher numbers or higher utilities. Okay, so we'll stick with our notation U with, and it now has the two arguments because any policy has two coordinates. And so this looks a lot like the consumer model, but now instead of talking about Cobb-Douglas utility, we're talking about, well, we have a decision maker with Euclidean preferences, and so what we're going to do is define quadratic utility. Remember that in the one-dimensional model, quadratic utility meant we looked at the difference between X and the ideal point, and we squared that, multiplied by -1. Now what we're going to do is we're going to look at the distance between X and the ideal point. We're going to square it and multiply by -1. So same exact idea. Again, here X is a pair, X1, X2. So this is called quadratic utility. As in the one-dimensional model. Remember, in the one-dimensional model, I sort of stuck with quadratic utility, but there was also another utility function we could use, which was just to take the absolute value of the ideal point minus the policy, and multiply that by -1. And we can do that here as well. That means we just look at this Euclidean distance, multiply -1. That's a perfectly good utility function as well, but you know, I just usually work with the quadratic utility. Okay. So now that we have, we've talked about the policy space, preferences, and utilities, which is related, we'll apply the optimality principle. Obviously, this politician will choose the best policy they can. Well, if they can choose their ideal policy, that's what they'll do. It's you know, a simple choice. Okay. So let me talk about some of the geometry of this a little bit more. Now, we talked about graphing a utility function in the model of the consumer, and I showed you a three-dimensional picture of that. And we can do the same thing in this two-dimensional policy choice model. What I would do is I would have a vertical axis for utility, and then I would take our two-dimensional Cartesian plane and lie it flat. Not so good. Like so. So imagine there's this flat plane coming out of the whiteboard. There's an ideal point P on that plane with coordinates P1 and P2. And then given any x on that plane, the utility is in this policy space. The utility, to get the utility, we look at the distance between that policy x and the ideal point P. We square that distance and multiply -1. So the utility is going to be negative. So if I were going to graph this utility function, it's going to actually be underneath that plane because it's going to be taking negative values. And then, to get the utility from x, we would go down until we hit that graph, and then we would go over to this vertical axis to get the utility from x. Okay, so that three-dimensional kind of picture, it's not the best to look at. So again, what we're going to do is we're going to think about a topographical map of this big utility hill, and so let's look on this hill at the policies. Well, basically, let's walk around this hill and maintain a constant altitude. So we would sweep out something like this red shape here, and now we're below the plane. So if we looked up, we would see, we would be underneath a bunch of policies that all have the same utility as x. Okay, so now let's look at that set of policies. So if this is P, and here's our x, that set of policies is going to be something like so. And right, so these are the policies that have the same utility as x, which means they're the same distance from P as x is. And so what I'm going to do here is just try to draw a perfect circle centered at that ideal point. That's not a great circle, but you get the idea. So, right? So for a given policy x, we're basically now just looking at the indifference curve through x. These policies all are the same distance from the ideal point as x is, so they have the same utility. So our decision maker is indifferent across all of the policies on this circle, okay? If we picked a different policy, like a y, here I'm picking a y that's closer, so that's going to be better. We could do the same exercise, and we would then look at the indifference curve through y, and that would be a circle, again centered at P, but now has a smaller radius. Circles are not doing well. And again, this politician is going to be indifferent between any two policies on that smaller circle, okay? But because that smaller circle, well, it's closer to the ideal point, so everything on that circle has a higher utility. So those are all strictly better for the politician than anything on this bigger circle. We could keep doing this. This whole policy space, the Cartesian plane, is just full of these indifference curves. And I shouldn't even try to draw more circles. So, and instead of drawing the three-dimensional picture, then we'll focus on just the two-dimensional picture with the indifference curves. So that gives an idea of the geometry of this two-dimensional policy choice model. In the next installment, I want to dwell on this model a little bit more. It might not be quite as common or easy to work with as the one-dimensional model, but it's clearly a more realistic model. And even if it's harder to work with, it's still important to understand, and we can still get a lot out of it. So that's what's coming up. I'll see you in the next one.